Hi, I'm Brandon Merrick.
And I'm Ian Evans.
And I'm Brian Barnes. And we are
Automated Servo Control.
This is a picture of our simplified block diagram. There are four main components to the block diagram, those being the control unit, the motor control unit, the LabVIEW unit, and the sensors block.
The system works in the following fashion. The sensors block takes in voltage signals and adjusts them based on the testing environment. The LabVIEW system then takes in the adjusted voltage values and converts them to digital values. In the control unit, it both receives the digital values created in LabVIEW and user input to allow the system to control the test environment. Control signals are sent out to a series of relays to adjust the motor.
Within the LabVIEW block is both the LabVIEW code and the LabVIEW existing system. The existing system sends out the control voltage to the sensors and reads in the adjusted voltage values from the sensors. These signals are converted to actual values in the LabVIEW code that can be easily displayed, transmitted to the control unit, and properly saved as a text file for analysis.
This is the LabVIEW existing system that connects the sensors and computer with the LabVIEW code. This PUT connection allows the LabVIEW code to send and receive voltage signals.
This flowchart analyzes the internal workings of the code. We will first look at the LabVIEW code portion. Once the program is started, the existing system will begin to send and receive voltage values. These values received will then be converted to actual values, such as pressure and displacement, that are then sent to the control unit, graphed, and saved on the computer. There are three main sensors that our system deals with: the transducer sensor, which reads the current values for the water pressure, the load cell sensor, which reads the value for the current load pressure, and the displacement potentiometer sensor, which reads the current value of the displacement.
This is a picture of the load cell, which is located at the top of the soil specimen capsule. This is a picture of the potentiometer sensor, which is located below the plate of the soil specimen capsule. This is the control board, which houses the transducer sensors. Other knobs and switches on this board are used to achieve the correct water pressure for a test as well.
The control unit is made up of a BeagleBone Black, a Linux PC about the size of an Altoids tin. This is powered by a power supply that converts 120 volts AC to 5 volts DC at 1 amp. It is also connected to the OSU network. Our test is launched by the command console, where the users input control information. From here, the control unit receives data via UDP communication about the test environment. After this, the software decides how to adjust the motor, and then adjust the GPIO pins accordingly. This is the hardware of our control unit. It includes the transformer, the power unit circuit, and also the BeagleBone, and their respective wiring.
This is the motor control relay block, which is made up of a series of solid-state relays. These relays are used for an AC load that needs to be controlled by a DC source. There are two types of relays, which are normally closed and normally open. The normally closed relays are used in conjunction with the switch to maintain manual operation. When a test is being run, these three relays are sent a control voltage that opens them, disabling the manual switch. The other three relays are normally open. During automated testing, these relays receive control signals that close the relays that correspond to the correct motor direction.
We're now going to demonstrate an automated test. This is what the master station looks like from the user's point of view. On the right is the LabVIEW graphs depicting the sensor data as it comes in from the existing system. On the left is the PuTTY terminal, which allows the user to enter command values. The user is first asked whether he wants to run a displacement test or a load pressure test. The value for pressure or displacement is then entered by the user. Then the user is asked how long he wants the test to be. Next, they're asked whether they want to run on station 1 or station 2. Then the user is allowed to enter the value for the selector position, which is located on the motor. Finally, the user enters an acceptable error margin for the test. As you can see, there are 2 tests being run and displayed simultaneously. Currently, the values for the second test are being entered into the system. The motor will either move up, down, or halt in order to keep the constant pressure or displacement needed for the test.
Currently being displayed is Station 1 attempting to reach its goal displacement value.
Here is Station 2 attempting to reach its goal load value. As you can see, the second test has reached its goal value of 1,610 pounds and has begun oscillating within the acceptable error margin. The system will continue oscillating until the end of the test. This is the motor of Station 2 oscillating around the goal load value of 1,610 pounds.
Tests like these are needed to prevent another Leaning Tower of Pisa. The reason why the Leaning Tower of Pisa leans is because the soil strength beneath the building is not strong enough to hold up the load.
When an automated test is not being run, the user can control the test by flipping the switch located on the motor control relay box. However, when an automated test is being run, the switch no longer works.